So, in today's video, we're going to talk about composite beams. So, why would engineers be interested in using composite beams? Uh, I think the the major reason that engineers are interested in using composites in general is that they typically provide very high strength relative to their weight. So, for an example, if we're talking about continuous fiber composites, which are often used in aerospace industry, for example, if you have a carbon fiber and epoxy composite, its unidirectional yield strength, so the direction along the fibers, can be as high as 1730 megapascals, which is incredibly strong, while its density of the composite is only 1.6 grams per centimeter cube. So, um, comparing that to a typical aluminum alloy that's used in composites, aluminum 2045, it is about 4 times stronger, granted along the continuous direction, and it's about 2/3 of the weight. So you're saving about 2/3 of the weight, and you have about a 4 times increase in strength. So the strength to weight ratio is like 7 times higher or so than of that of aluminum. So that's an incredible savings in weight, which improves efficiency overall of the structure and gives you a little bit more freedom in your design. So so when we're talking about composite materials, what we're going to be looking at is we're really concerned. It's really our composite analysis is really based off of Hooke's law. So if we have a composite material that both has two materials in it, uh, one material and one material is going to be stiffer than the other material. The stiffer material for a given strain will experience a higher stress. Okay, so so if in this case where we had a fiber and a matrix, the fiber is much stiffer than the matrix, so the stress within the fiber of our composite is going to be much greater than the stiffness in the matrix. Okay, um, so what we're going to be looking at today is that we're going to be looking at composite beams, and what we're going to do is um, we're going to evaluate the stresses within the composite beams. We're going to create something called an analogous cross section or an equivalent cross section of a single material. So from this, all right, what we're looking, so what we're gonna, so using this single beam, we can then determine the stress and displacement. So with the equivalent cross section, we can calculate the stress and the equivalent displacement within the composite material. Um, so if, for example, we have a cantilever beam here that has two materials, material 1 and material 2, we'll say that material 2 has a greater stiffness than material 1. Okay, and we're given the dimensions of the beam as having a width b, and it has the thicknesses of our two materials are h1 and h2. Okay, so what we're going to do, so what we're going to do is we're going to create an equivalent cross section based off of this system. Okay? So we're basically going to convert this to a one material beam. All right. So we're going to determine an equivalent cross-sectional area for the composite beam using the less stiff material. So that's in case material 1. All right. So what we're going to do is we're going to add more material 1 while maintaining the strain behavior of the original composite beam. Okay. So for simple bending, we know that strain is equal to stress divided by modulo less elasticity. All right. And we know that our bending stress is equal to negative my divided by iz times divided by e. Okay. So based off of this equation, what we notice is that our stress is is only a function of the moment of the of x. So along the length, the moment might change. All right, and then the second thing it could be a function of is y, which is like the position within the location relative to the centroid. All right. Therefore, what we can say is that the width of the beam can be modified. All right, because this is independent. The strain it would be independent of B. Okay, so so if we start off with a composite, our composite cross section here that has, we'll have it as, it has two materials, E2 and E1. Remember that E2 is greater than E1. All right, and then we have two the thicknesses of the two materials are going to be H1 and H2. All right, and then the width of our, so what we're going to do is we're going to find an equivalent width of our section. So our equivalent width is going to label that as BE. Okay, H2 will remain the same here, and H1 will remain the same. Okay, so we're going to convert this composite cross section into an equivalent cross sectional area of just material 1. All right. All right. So we will then adjust the width of the equivalent cross sectional area to maintain the equivalent strain. Okay. So we know that the equivalent cross section, we're going to say, must have the same strain as the strain within the composite. Okay. So using Hooke's law, what we can say is that the strain within the equivalent composite sigma x e divided by the elastic modulus of um, of uh, of material 1 must be equal to the strain, the stress within the composite material divided by E2. Okay? So from that, we can say that the stress within the composite would be equal to the ratio of E2 over E1 times the stress within within the equivalence section. All right, and then we can write that stress within the equivalence section is equal to minus my over IZE, where IZ is the equivalent moment of inertia for the equivalent section. Okay, so in order to determine the stress within our composite, we have to determine what IZE, okay, would be equal to, and that's going to be dependent on the equivalent width of our composite. Right? So, and the second thing that we need to know here is that for this system to be equivalent, the total force over the stiffer regions of the material 2 and the equivalent cross section must be the same. Okay, so the force of these two sections have to be equal. So the force within the composite has to be equal to the force within the equivalent section. Okay, so so we can rearrange this and we can solve for the equivalent width BE. All right. All right. So BE, right, could be equal to sigma x c BC delta y divided by sigma x e delta y. All right. So delta y's will cancel out. And we'll be left with, if we plug in our values of sigma xc and sigma xe, what we'll end up getting is we'll just end up getting E2 divided by E1 times BC. Right? because the stress is just going to be equal to the strain within the composite sections, and the equivalent section are equal to each other. So the only thing that changes is the elastic moduli. So we can then, so since E2 is greater than E1, we know that BE must be greater than BC. Okay? All right. All right. All right. So now that we know how to calculate BE, we can create an equivalent cross-sectional area. So, all right. All right. So within our equivalent cross-section, what we'll notice is that the equivalent cross-section it's all made out of material 1, while the original composite section had our two materials, E1 and E2. Okay, so between these two regions where we have our same original material, all right, the stresses are the same within this region. Within the other region of the beam, the stresses will not be equivalent. All right, so the stress in the equivalent section here will underestimate the stress that's actually going on within the second material E2. Okay, so in order to calculate the stress within the composite area or within material 2, we have to multiply the stress within the equivalent section by the ratio of E2 over E1 times the stress within the equivalent section here. So whatever stress we calculate in this region here, we need to multiply it by E2 E1 to get the stress within this region here. All right. All right. All right. So a few last notes. In the case of if you have a curved section, the equivalent width may vary as a function of height. All right, and then you can adjust for this by accounting for the equivalent area and the equivalent moment of inertia, which only vary linearly with the change in width. So we can say that the area equivalent would be equal to, again, just the ratio of E2 over E1 times the area of the composite, and then IZ of E would just be equal to E2 over E1 times IZ of the composite section. Okay? So, alright. So, if we know the equivalent area and the equivalent moment of inertia, we can calculate the equivalent stress for both axial and bending loads. And then the last thing is that if we have, for deflections of composite beams, what we will do is you'll use the equivalent cross-sectional area to determine the moment of inertia, and you can then use the elastic modulus of the equivalent cross-section as well in the bending equations to determine the deflection. All right. So we're going to do an example problem that will illustrate how we can apply this to a composite section. These methods to composite sections determine the stress within both an aluminum and steel composite.